Уважаемые коллеги, 11 часов. Я несколько слов скажу сначала о нашем семинаре. Значит, сейчас мы заслушаем, это, можно сказать, отчетные доклады наших китайских коллег, аспирантов из Технического университета Шанхая. Они к нам приехали с тем, чтобы продолжать работать над своим проектом. И фактически их PhD заключается в том, что они проводят моделирование циклотрона на энергию около 11 МЭФ для ПЭТ-томографии. Это сверхпроводящий циклотрон, сверхпроводящие обмотки, остальное все теплое. И сюда они приехали для того, чтобы, во-первых, проверить свои расчеты, сравниться с нашими методиками, чему-то научиться. У нас вот Ву Юэ, он, значит, занимается ВЧ и работает здесь под руководством Семена Гурского. dlnp.jinr занимается динамикой расчетов магнитов, работает под руководством Олега Карамшева. Нам, какой наш интерес? Ну, во-первых, просто collaboration, сотрудничество ради того, чтобы видеть, как другие разрабатывают эти самые ускорители, для того, чтобы видеть, какие методики применяют китайские коллеги, а они уже, вы увидите их уровень, это хороший уровень разработок. И для того, чтобы в какой-то степени, может быть, нам удастся еще сравнить наши расчеты нашего ускорителя, наши китайские коллеги, как альтернативная команда проведут расчеты и нашего ускорителя тоже. Сейчас прошло полгода с тех пор, как они работают у нас в отделе, и по формальным, скажем так, они обязаны провести отчетный доклад. Так что у нас это и как отдельское мероприятие, нам просто интересно послушать, что же они уже сделали и за эти полгода, и чем занимаются, и как чисто формальное мероприятие, которое мы обязаны провести. So now I'll ask our Chinese colleague, Wu Yue, to make his report, and please welcome.
Hello everyone, my name is Wu Yue from China. The report of today's presentation, the title of my report is Research and Design of the RF Cavity for an 11 MeV Superconducting Cyclotron. The main contents of my report are divided into 3 parts. Firstly is background, and secondly is research and design of the RF cavity, and thirdly is coupling system of the RF cavity. In order to produce enough medicine isotopes, and the cyclotron are the most commonly used accelerators for the production of the pads. And so our design goal is to develop a compact cyclotron for 11 carbon and 80 fluorine single dose production. And according to the requirements of the isotopes, and it's necessary to ensure the beam energy is greater than 8.5 MeV and the beam current is greater than 10 microamps. It also requires the cyclotron to meet some conditions such as single dose production, minimum size and weight, and another conditions. And based on the beam energy and the radius, as well as the compactness requirements, so we need a high magnetic field. So we adopt a superconducting magnet. And the final scheme is a low energy compact superconducting cyclotron. So the final the beam energy is determined to be 11 MeV, and the beam current is determined to be 15 microamps. And the main system of the cyclotron contains a RF system, iron source, magnet system, and extraction, and a cryogenic system. My research are focused on the RF system part, includes the RF power generator and the RF cavity. The main research contents of the RF cavity are as follows, including the research and the design of the RF cavity and the frequency tuner and the RF input coupler and the multifix simulation. The first part is about the research and the design of the RF cavity and using the equivalent circuit method to verify the result. And according to the design requirement, we can design the main body of the RF cavity and simulate it, obtain the resonant frequency, Q factor, and other characteristic parameters. And after determining the main body of the RF cavity, and based on the transmission line theory, the entire resonator can be equivalently regarded as a multiple section of the transmission line. For example, in my model, the main body of the RF cavity can divide into 4 parts of the transmission line, including the round coaxial transmission line and the transition transmission line, and 2 parts of the rectangular transmission line. And we also can get the equivalent circuit diagram of the RF cavity. And in order to determine the resonant frequency of the RF cavity, we can solve this circuit. And by the admittance method, we can choose any surface in the circuit as a reference surface. At the reference surface, the total electrical admittance is 0. And from this condition, we can get a transcendental equation. And based on the calculation formula of the input impedance or input admittance, we can get the total electrical admittance at this reference surface. And based on the calculation formula, we can get a transcendental equation contains the resonant frequency. And in order to solve this transcendental equation, we need to determine all the characteristics parameters of each transmission line, including the characteristic impedance and the transmission line length and the equivalent capacitance. And we can calculate all the results by using the following formulas. And the formula 1, 2, and 3 is calculation formulas for the coaxial transmission line to calculate the characteristic impedance. And the calculation formula 4 and 5 is the calculation formulas for the equivalent step capacitance. And after determining all the parameters, we can substitute them into the transcendental equation and obtain the resonant frequency and compare it to the simulation result. And this part is a calculation and verification. The first step is to verify the influence of the parameters of the round coaxial line on the resonant frequency, include 3 parameters, length of the line and the outer conductor radius and the inner conductor radius. From the calculation result, we can see the results of 2 methods are basically consistent in general. Just when we change the inner conductor radius, it will give us a big error. The biggest error can reach 2.7%, because when we calculated the characteristic impedance of the transmission line, the average value are used. And if we adopt this method to get the impedance, it's necessary to ensure the size of the 2 ends of the transmission line and to be similar. But if we change the inner conductor radius too much, it will bring the deviation in the characteristic impedance and result in the deviation in the resonant frequency. And the second step is to verify the effect of the parameters of the transition line and the rectangular line. From the picture, we can see the calculation result of the 2 methods are basically consistent, and the biggest error is not exist 1%. So we can adopt this equivalent circuit measure to guide us to design the main body of the RF cavity and save the simulation time. And this part is about the structure analysis of the RF cavity. And in order to reduce the maximum field strength in the cavity, I have added some round corner or around the disk edge. And by changing the radius of the disk edge fillet, we can change the electric field strength in the cavity. And from the picture, we can see if I increase the radius of the disk edge fillet, the resonant frequency change very slightly, but it can significantly to reduce the maximum field strength. And I also try to compare two types of stem. In the left picture, we can see one is a rectangular stem and another is a circular stem. During the design stage, it's better to ensure the radius of the circular stem is not too large to avoid the additional impedance. And from this picture, we can see if we adopt a circular stem, the resonant frequency is not exist 46 MHz, but at the same length, if we adopt a rectangular stem, it's easy to reach the 46 MHz. But what's more, at the same condition, the resonant frequency with a rectangular stem is greater than the circular stem. Because the characteristic impedance of the circular stem is bigger than the rectangular stem, it will cause the resonant frequency decrease. And according to calculation formula of the circular stem, we can know if we increase the radius of the circular stem, the radius will decrease and the impedance will decrease. It will cause the resonant frequency increase. But if the radius of the circular stem change too much, it will bring some step capacitance. From the calculation results, we can know if the capacitance change from the 1 pF to 10 pF, the resonant frequency will change from 45 to 42. But if the capacitance change from 10 pF to 100 pF, the resonant frequency will decrease rapidly to the 26 MHz. It's a not good choice. So in our design, we adopt a rectangular stem to avoid this situation. And the second part is about the coupling system of the RF cavity. Due to the exiting of the tuner or RF input coupler, the RF cavity will have a perturbation. And this perturbation can equivalently regarded as a small change in the shape. And according to the micro circuit, we can get a perturbation formula. And according to the formula, we can know if copper components located in a weak magnetic field and a strong electric field area, the resonant frequency will decrease. But if the copper components located in the strong magnetic field and weak electric field area, the resonant frequency will increase. So according to this rule, we can decide to place our copper components at the proper position. And according to the microwave circuit theory, the entire RF cavity can equivalent to a parallel RLC circuit, and the inductive copper components can equivalent to a series inductor. And from the circuit, we can get the input impedance. And when the resonator is resonance, we can get the expression between all the characteristic parameters. And the left picture it shows the overall design of the RF cavity for the copper system. And includes two types of tuners and one RF input coupler. And the right picture shows the insertion position of two types of tuners in the round cavity. And this two pictures shows the influence of the tuner insertion position on the resonant frequency. And due to the magnetic field distribution of the round cavity is centrally symmetric. So if we insert a type 1 tuners at any position on the same circle, it will bring the same effect. So from this picture, we can see if we insert a type 1 tuners at any position on the round cavity, the value of the resonant frequency change is the same. And this picture shows that if we insert a type 2 tuner into the bottom of the round cavity, the RTF have an inverse relationship with the resonant frequency. And these two pictures shows the influence of the tuner radius and the insertion dips on the resonant frequency. From the calculation result, we can see the type 2 tuners has a great impact on the resonance than the type 1 tuners. And it also have a larger range frequency tuning. So during the design process, we can combine two types of tuners to achieve a coarse and precise frequency tuning. And by changing the tuners and the insertion dips of the type 1 tuners, we can achieve a precise adjustment. And by changing the radius and the insertion dips of type 2 tuners, we can get a coarse adjustment. So based on the two types of tuners, we can achieve a wide range and precise adjustment. We also can perform a polynomial fitting based on the calculation results, and we can get the formula between the frequency change and each structure parameters of the structure tuner. And when the radius of the tuner are determined, they are just the insertion dips can affect the resonant frequency. And due to the symmetry of the round cavity, so the M and N respectively represent the number of the two types of the tuners. And during the design stage, if we can have an equivalent formula to predict the resonant frequency and equivalent inductance, it will simplify our design process and saving the simulation time. So according to the equivalent inductance of the tuner is a very small value, and according to the equivalent circuit, we can get this formula. And based on the above calculation result, we can know the resonant frequency and the RTF have an inverse relationship, and the F is found to be proportional to the insertion dips LH and the square of the small RTF. Therefore, the equivalent inductance LC can be inferred as this formula. And in the formula, this part is a correction term. And according to the equivalent inductance of the tuning structure is a time quantity. So we also can have some big mistake, have another calculation result. And based on the two calculation formulas, we can compare the conjectural formula results and simulation results. And this part is calculation and verification. The first step is to verify the influence of the insertion precision on the inner conductor equivalent inductance and the resonant frequency. And from the picture, we can see the calculation result of the two methods are basically consistent. And the biggest error is not exist 0.1%. It's a good prediction. And the second step is to verify the effect of the radius of the tuner and the insertion dips. From the first picture, we can see the results are basically consistent, but when we change the radius of the tuners, the prediction of the inductance is not good. It will give the biggest error is 3%, but the value is acceptable. And in the study, we usually concentrate on the prediction of the resonant frequency. And from these two pictures, we can see the biggest error is not exist 0.1%. So during the design stage, we can use the conjectural formula to guide us to design the tuner structure and give us a reference during the frequency tuning. And this part is about the design of the RF input coupler. The left picture shows the electromagnetic calculation diagram, And the right picture is an overall conceptual design diagram of the RF cavity. And the power coupling method adopts inductive coupling. And the whole structure of the RF input coupler consists of the a coupling loop and a transmission line and RF windows. So if we want to get the best impedance matching, it's necessary to ensure the coupling loop placed to a location with a strong magnetic field. And because the strong magnetic fields of the RF cavity are concentrated on ends of the stem, so we need to place the coupling loop near the inner conductor of the round cavity. And in order to increase the coupling loop area and the effector magnetic flux, the coupling loop adopt a curved design, which can help us to improve the coupling efficiency. And in order to ensure the structure of the coupler meets best impedance matching, we use a S11 parameter and the coupling coefficient beta to measure it. The coupling degree between the RF cavity and the RF input coupler are calculated by this formula. And in the formula, the Q0 is unloaded quality factor of the RF cavity. And the QE is external quality factor of the RF cavity. And the PI is the reflective power, and PF is the forward power. And according to the value of the beta, we can divide it into 3 states. When beta is smaller than 1, it's under coupled state, and beta is bigger than 1, it's over coupled state, and beta is equals 1, it's critical coupled state. And during the design stage, when it's necessary to ensure the RF input coupler to meet the critical coupled state to achieve the maximum input power. And in order to determine the best impedance matching position of the RF input power, scanning calculation about the insertion position are calculated. And in order to get a smaller S11 parameter, I optimize the structural parameters of the coupling loop, including 4 parameters: insertion depth of the first section and the second section, and the length of the deviation from the middle plane in the positive direction and the negative direction. And this picture shows the structure parameters of the coupling loop on the S11 parameters. From the calculation result, we can see if the value of the structure parameters are proper, the RF cavity and the RF input coupler will achieve the best impedance matching, and the S11 will very, very small, and the coupler degree is equals 1. But if increase the value of the structure meters, the S11 will increase, and the coupler degree will increase too. Because when by observing the magnetic field distribution around the RF input coupler, we can know if the RF input coupler set a over-coupled state, the magnetic field around the insertion position will weaken, and the effective magnetic flux passing through the coupling loop will reduce. So it will cause the S11 parameter increase. And this is about the transmission line. The transmission line adopts a 15 ohm coaxial transmission line, and we adopt a tapered transmission line to achieve the transmission line with a small radius transition to a larger radius. And the main function of the tapered transmission line includes 2 parts. One is it can reduce the impedance discontinuity effect, and it also can increase the parameters for adjusting impedance matching. And this picture shows the influence of the transmission line structure parameters S on S11. And the radius between the top and bottom of the tapered transmission line are defined as a big S. And from the calculation result, we can see the size of the S has a great impact on the S11. So we can, by changing the size of S to achieve the best impedance matching and get the maximum input power. And in order to improve the impedance matching of the RF window, the RF window adopt a multi-stage design, including the power input segment A and two coaxial transmission lines with the same line structure parameters and the RF window. Where the RF window materials is aluminum, and during the design stage, it's better to ensure the radius of the interconductor of the RF windows are consistent with the interconductor radius of the transmission line to avoid the additional discontinuity effect. And this picture shows the influence of the R window structure parameters on S11, where RB and LB represent the outer radius of the and the length of the transmission line in segment B or D. And the RW and LW represent the outer radius and the length of the RF window. And according to the calculation result, we can see the structure parameters of the RF window have a great impact on the S11. And if the value of the structure parameters are proper, it will give us a bad S11 result. The best result can reach negative 18.2 dB. It represents the reflection power is very small. And this part is about the multiphase simulation. According to the design requirements of the acceleration voltage, I have calculated the relationship between the RF input power and gap voltage. And according to the design requirements of the gap voltage is 30 kilowatt. So we can determine the value of the input power is about 4.6 kilowatt. And then based on the temperature distribution of the RF cavity, I have designed the coupling system for the high temperature area. Includes 3 tubes, 1 cooling tube for storm, and 1 cooling tube for cavity, and 1 cooling tube for capsule. And this is by using the console to do a multiphase simulation, and includes the electromagnetic simulation and heating analysis and structure analysis. According to this picture, we can see the temperature distribution of the RF cavity. We can know the high temperature are concentrated on the area without the cooling tube, especially on the D. And the maximum temperature can reach around 16 degrees. And this picture shows the deformation of the RF cavity, and the biggest displacement is around 0.23 millimeters. And according to this picture, we can know the effect of flow velocity on the maximum temperature and the maximum displacement and the frequency drift. And according to the calculation result, we can see the frequency drift change from the 34 to the 44. So the biggest frequency drift remains within the frequency tuning range. So it represents our design. Maybe it can work. And that's all contents of my report. Thank you for your listening. Thank you.
Thank you for your report. And questions, please, colleague. I just want to, while the colleague will think about their questions, I'll just want to advise you to put numbers on your slides, because not just now, but yes.
Okay.
to have possibility to ask questions. I have one question. When you calculate multiphysics, you use CST, COMSOL, or what?
Both.
Both.
Yes, both.
And you compare the results?
Yes, the resonant frequency is similar.
Yes. And another question. When you calculate temperature distribution, do you see how RF window?
RF window.
Temperature
is
RF
very
window.
small.
Very small. And
Yes, because I put a cooling tube around the RF cavity, surrounded it.
Where cooling tube? Around?
Passing through the coupling loop.
Through the coupling
passing
loop.
through the RF windows.
Thank you. Maybe anyone else?
Can you tell the value of temperature without the cooling tube? The value of the temperature of the coupling loop?
Coupling loop.
Without cooling?
Without cooling, I don't sure, but the temperature is very high. Maybe 600.
Thank you. And да.
Все электротехнические расчеты полезно было бы приложить к фазотрону. Там как раз такая противодуантная рамка, дуант.
Фазотрон?
Посмотреть, что
Зачем он нам?
где будут точки, вот эти расчетные, на тех цифрах, которые есть на самом деле.
Да ну, сейчас фазотрон невозможно посчитать. Где он тот фазотрон? Sorry. Ну, это потом мы обсудим тогда. Хорошо. One more question I would like to ask you. Have you changed any parameters of the cavity, geometrical parameters, to have a higher quality factor? Or you need not?
The Q factor about 6,000. And I changed the parameters of the cavity to achieve a better better Q factor.
And have you possibility to change it substantially because you are restricted by magnetic system? And do you influence on the magnetic system? Maybe you say to her that...
I talked to Pan and maybe limit the height of the cavity is not too big.
Okay. Thank you. Any more questions?
And who played a major role in your work? Because when you, for example, if you need to have more height for your cavity, and she tells you, no, magnetic system will not allow you to get more. So who wins in this situation? Can she allow you to have a
compromise?
Compromise.
So in this case, so can you let him use more space? Yes, this gap. Can you allow him to have more space, or you're limited also for your situation?
Oh, she will tell us. Okay. I think we will ask to her after her report. Maybe we will thank you, our author, once more.